Hello and welcome to inverse functions. This is a really fun diagram of what's going on. It looks like apples are going in for the function, and then an operation is happening that you get the inverse, and yet you can still get the opposite in the end once the inverse operation comes about. So let's get started. Let f and g be two functions such that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. The function g is the inverse of the function f and denoted by f inverse. Thus, f inverse of x equals x, and f inverse of f of x equals x. The domain of f is equal to the range of f inverse and vice versa. So for this example, find f of g of x and g of f of x, and then determine whether the pair of functions of x and g are inverse of each other. Okay, so if we get started by A, which is finding f of g of x, we have the function f of x equals 8x, and g of x equals x divided by 8. So, to get started with A, we're using compositions of functions again. So we want to start by writing the part of the f of x function without having the x in there. So we'll start off with just 8, which is the beginning part of the function, and then in place of x, just write the g of x function, which is x over 8. So what we did was start off by writing the non-variable portion of the f of x function, and then for the variable part, we just replace it with the g of x function. And if you notice, the two 8's will cancel out due to cross multiplication. Think of it like this: the 8's will cancel out, leaving you with just x. Okay, doing the same thing for part B, which is g of f of x. Write the g function, replacing the x portion, which is on top, with the f of x function. So here's g, replacing x with open set parentheses, and in those parentheses, write just the f of x function. Okay, and if you notice, 8x over 8, the 8's will cancel out, leaving you with just x. And since we're both able to get x from these two, these are inverses of each other. Okay, moving on. Finding inverses of a function. So we'll replace the f of x with y in the equation, interchange x and y, solve for y. If the equation does not define as y as a function of x, the function f does not have an inverse function, and the procedure ends. If the equation does define as y of a function of x, the function f has an inverse function. If f has an inverse function, replace y by f inverse of x. Verify results by showing that f of f inverse of x equals x, and vice versa. So, to do this, let's get started solving f of x equals x plus 10, and find the inverse of that. So, we have our f of x equals x plus 10. Our first rule says replace f of x with y, so just write y in place of f of x. Okay, for the next step, it says to interchange x and y, so where y and x are, just change their placements. So we have x equals y plus 10. Okay, solve the equation for y. So let's subtract y on both sides. So we have negative y plus x equals 10. Now to get y by itself, subtract x on both sides. So we have negative y equals negative x plus 10. Now finally, to get just a solid y by itself, you can multiply a negative 1 on both sides of the equations. So you're going to be left with y equals, we're going to have a positive x minus 10. Okay, so it looks like that will be the inverse, so now we can replace y with f inverse of x equals x minus 10. Okay, moving on. One can also tell by looking at the graphs of a function whether or not an inverse function exists. The horizontal line test for inverse functions. Okay, a function f has an inverse of that function if there is no horizontal line that can intersect the function of the graph f at more than one point. Okay, for these examples we have three graphs, and we are going to determine if the graphs represent functions that have an inverse. To do that, all you have to do is draw a horizontal line through the graph, and if it hits more than one point, then it does not have a function. So to test that, look at this first one, this is parabola. We draw a horizontal line, you see it intercepts here and here. It hits more than once, so it does not have an inverse. Not an inverse. It does not have one. Okay, if we look at the second one, which is like a linear line, it does have an inverse. So inverse possible. Okay, and if we look at this last example, looks like that's going to be a cube root of something. You can draw a line horizontally anywhere, and you can tell that it will not intersect more than once at any place. So this has an inverse possible. Okay, continuing on with this discussion, I believe this will be our last topic for this video. We are going to graph the inverse of a function. The ordered pairs are reversed. The graph of y, or f inverse of x, is a reflection of the graph of y on the line y equals x. So sketch the graph of the inverse function. Okay, so here, graph on the four-quadrant plane, we have a line, a linear function, and the original points that can be looked at would be 6, 0 and 0, -6. So all we have to do is reverse the x and y points. So we have 6, 0. We just to rearrange those, we have 0, 6. And if we graph that, it's going to look like the point right here. And if we have 0, -6, we can just reverse it to be -6, 0, which looks like the point would be right here. And if we connect those two lines, that will be the inverse of the function presented graphically. All you have to do is reverse the coordinate pairs.